Hello, everyone, and welcome to today's CCP Volume EM Show and Tell. My name is Helen Spiers, and I've been co-hosting this series with Martin Jones, who is PI of CCP Volume EM, and he is also on this call as co-host. Thank you very much for joining us. We're delighted to have you with us for this session, where we'll be hearing from Rocco D'Antuono from the Francis Crick Institute. Today's talk is titled Napari Software for 3D Segmentation with the napari-zelda plugin. So Rocco will introduce us to Zelda, an open source Napari plugin designed to make 3D image segmentation and bioimage analysis workflows more accessible, interactive, and user-friendly. The session will be particularly valuable for anyone interested in microscopy data analysis, especially those who want to explore 3D segmentation without needing extensive coding experience. So Rocco brings a wealth of expertise in microscopy, bioimage analysis, and software development. He studied physics in Milan, specializing in advanced biospectroscopy, and has since worked across leading research institutes in Italy, Switzerland, and the UK. Since 2018, he has been part of the Crick Advanced Light Microscopy platform, where he works as principal microscopist and bioimage analyst, supporting researchers with microscopy, image analysis, and training. Alongside his work on imaging techniques, he has also been actively involved in the wider bioimage analysis community. He is a fellow of the RMS, a founding member of New Bias Academy, and has contributed to the development of Global Bioimage Analysts Society. Before I hand over to Rocco, just to note that this session will be recorded and it will likely be shared on the YouTube channel. And with that, I'm very pleased to welcome Rocco today, and I'll now hand over to him. Thank you, Rocco.
Thank you very much, Ellen, and thank you very much for the community to having me here to present today. So I'll start sharing the screen and start with the presentation. So today I will present a plugin for Napari called the napari-zelda, and then we will attempt a short live demo on how to use it. So I'm going in presentation mode. I hope slides are visible for Ellen and the rest of the audience.
Yes, it looks good, Rocco.
Okay, thank you. Zelda is a plugin for Napari that can be used to segment 3D image data of optical fluorescence microscopy. And actually, there is a bit of reasons behind developing it, at least for me personally. I started using Napari because of its capability to show data in a multidimensional way. Indeed, if one has ND dataset, can easily show reslice of volumes, or can explore the data in a temporal dimension, and also visualize a more complex experiment. Also, Napari is based on the use of libraries that are available in the Python environment. Very famous one, scikit-image, in order to do image segmentation, NumPy to handle numeric array, pandas or data table in order to handle data frames. So because of the availability of this library, it makes sense for me trying to develop a plugin where simply with click and point and click tool, I could try to repeat segmentation of the image data rather than writing a script or trying to edit every time the software. This was also triggered by the fact that there are many surveys that have highlighted how the community wants open source point and click software, and there is need for better software in order to handle 3D volumes and do tissue histology analysis. Also, the availability of software is overwhelming. So if one has no experience, it's very difficult to identify what is the right tool to use. There are databases like b.eu that aim to categorize software tools, and they are basically maintained by the community, so everybody can create a page about software and can describe the applications. Anyway, it's difficult for a person that has no experience in coding to navigate this world. So I tried to tackle common problems, like, for example, the one of counting objects in 2D or segmenting objects in 2D and relate bigger objects to smaller objects. For example, in the images you see in panel A and B, one question could be the one of segmenting cells and count, for example, how many mitochondria there are inside each cell, and eventually also measure the size of those organelles. In 3D, the same thing happens. One could have images where the nucleus is stained with DAPI, and then there might be spots that have to be counted. This might be RNA particles inside the cell nuclei, or eventually one could have, like in panel C, a tissue where a particular region of the tissue slice have to be segmented in order to count anatomical structures. When I tried to develop the plugin, I thought that these are very common problems, and I tried to find a solution using Napari. Therefore, I developed Zelda. Zelda is basically relying on the use of Napari, and I have added a graphical user interface component that will simply guide the user through a process of segmentation. In my view, this is quite versatile because you can segment objects in 2D or 3D. You can categorize objects using the parent-child relation, meaning that you can attribute the existence of smallest object inside bigger object. And I also tried to make the graphical elements available to allow the user to compose a customized workflow. Indeed, every block of the graphical user interface is encoded in a JSON database, and one can build up a graphical user interface that only contains the components that are needed for a specific workflow. It is reasonably limited in the sense that it doesn't do anything, relies on a very simple algorithm in order to segment objects. And I tried to benchmark it also against widely adopted, if not the most adopted software in the bioimage analysis community that are ImageA and Cell Profiler. So I was mentioning that the workflow is very simple. I could define it as I would say the most basic approach that one could have to segmentation. There are images in grayscale, as they can come from fluorescent microscope. These images might show intensity that is not homogeneous. Therefore, one could use the image contained in panel C, apply a Gaussian blur filter in order to homogenize the signal and obtain the picture in panel D. The further step would be threshold and create a binary picture. This is contained in E. In order to segment object, a common way would be to apply a distance map. This function identifies pixels and attribute an intensity that depends from the distance they have from the edge of the object in the binary picture. These points are used in order to generate seeds. This appears in the image G. And the final step is the watershed algorithm will use these seeds in order to drive an expansion and categorize a pixel belonging to the same object by labeling them with the same numeric value. So the result will be appearing in the panel H. Finally, one could be interested in measuring those objects. So it is important also to have the possibility to do very quick plot like histogram and scatter plot. I must say this is not something that was invented by us, but is basically the typical workflow that is used in very common software packages. For example, we got inspired by MorphoLibJ. Also in Cell Profiler, if one had to write down a pipeline, we'll compose it in a similar way. So we simply translated this into the world of Napari and added also the possibility to relate objects following the parent-child relation. I made the example, one could be interested into segmenting cells. So you can see in the second row, there are cells labeled with a different ID and could be interested in segmenting organelles. Finally, one could relate how many organelles or particles or smaller objects are contained in a bigger object and label them by the number or the ID of the parent cell. The plugin is capable of doing this. Finally, with the results that are produced, one could plot histogram of a specific feature or eventually scatter plot in order to trying to identify different subpopulation in the segmented objects. I tried to benchmark this software in terms of what was the mask that was produced. I've done it, for example, in 2D, trying to compare it with ImageJ and Cell Profiler. And I've also tried to measure what would be the execution time. Of course, here we are not comparing software that works in the same way. For example, if we compare the execution of a workflow graphically, simply clicking through buttons, this could take more time than running things in batch. However, I try to compare what is the experience of the user using different software and what is the average time that one would wait in order to obtain results. Eventually, you can see from the data that, for example, if one aims to run in test mode a pipeline in Cell Profiler, would have a sort of experience that is slightly slower than clicking things through the napari-zelda plugin. This is due to a different factor, but for me it was an example of how the user would feel and how much time would be spent in order to test the workflow. I will explain later how the functions that are used inside the plugin can also be used in a Jupyter notebook in order to do batch processing of data. So the goal of the plugin is simply to see visually how the result would be using Python libraries in order to segment objects and relate them. And one can think of later writing down a Jupyter notebook using the same parameter that have been used in the graphical execution and try to run batch analysis. We mentioned that the different blocks of the software can be accessed into a database, and eventually one can try to develop what I defined as a protocol. That means a part of the graphical software, and try to combine these different graphical components. Eventually, if one wants to add a new block, making use of Magic GUI library in order to create some widget for Napari, this can also be added in the list of the available blocks. So the plugin can be enriched also by users if they want to write a graphical part, and this can be integrated in existing protocols. The installation happens as usual through Conda. So one would get first a version of Napari, and then there is possibility to pip install downloading the latest version of the code from GitHub. So this would be done with the pip install git plus and the address of the GitHub page. I want to thank the co-authors of this work, but also reviewers and editor that during the process of publication pointed out, on how the code could be improved. And also I want to thank the first users, adopters from different university who provided a very useful feedback on how to implement the software. At this point, these are additional slides where I want to mention that the function that I'm using to build the graphical user interface rely on the use of Magic GUI. So Magic GUI is a library that simplifies the use of graphical elements so that they can be used in order to build an app that is relies on Python. We make use of this in order to create widgets in Napari. And it is the first type of approach that one that has a not in-depth experience in creating plugins would use. Of course, if one is expert, makes much more sense to develop a plugin relying on the Qt library directly. But I think that the decoration of function with the Magic GUI is simply helping testing and helps to start developing things. Here you have an example of a function. In this case, the block below from line 70 to 77 is creating an image that is the threshold version of a grayscale image. And you can see that above there is a part of code from line 63 to 69 that is a decorator that says you have to interpret this function with Magic GUI library, and one can feed in also elements that might be a label, might be checkbox or buttons inside this block. So this part above the decorator makes possible to transform a script that would use the function that is below between line 70 and 77 into a widget, so it means a graphical element that will appear in the Napari interface. The plugin is developed trying to make this for all the different components. Okay, so at this point, I finished the presentation. So what I'll do is I will try to launch the software that I have installed in a workstation. So the installation can be done with Conda. We said we will use Conda, but if you visit the website, Napari website, you can find also installation and different method in order to get the software working. So we will create an environment that, so if we want to install, you will create an environment that has Python, a specific version of Python 3.11, then activate the environment. And at this point, the software can be used with the Conda installed, selecting the channel Conda Forge in order to get Napari and PyQt library. Once this is done, the software can be launched starting the Anaconda prompt, and we will type Napari. So this should start the software. I will spend a few minutes in order to navigate different commands inside Napari. And these are not part of the plugin. It's just a way for me to show you the functionality of the software. And later I will try to use the plugin in order to segment some data set. So as you launch the software, this appears in this way. As you see, it is very simple as interface. Many of the function might be under some command, but actually what a positive point of view for me is that it starts very simple, but one can enrich the graphical user interface building widgets or installing plugins. We refer to standard data set. So this could be, for example, the cells 2D, 3D. In this case, the data themselves are loaded as two separated layers. So the concept of layers here in Napari is that it makes sense to put together all the data that one wants to handle together. For example, if we have a Z stack like this, makes sense to have all the data belonging to different slices of the Z stack because we might want to segment them all together, whereas the other channel, the membrane, will appear in a separated layer because it's a part of an element that we want to handle in a separated way. Now, with these tools, we make visible different layers so we can go through the Z stack, or we can visualize in 3D the object, and I'm using now what correspond to the mouse wheel in order to zoom in, or clicking and rotating in order to explore the data set. At this point, we can change, for example, the brightness and contrast here with contrast limit in order to highlight features. Actually, this does not modify the underlying data. Or eventually, we can try to use a different lookup table for the object. Or we can try to create new types of layers. I will try to create this a new type of layer that is called the labels. And in this case, I will hide what are the other channels. So I'm now looking to the nuclei channel, and I'm showing the data in gray. If I switch to the visualization, this tool of labels can be used in order to manually annotate data. So what I'll do is I select this layer that is now a label type. You can see there's a small icon of a tag here. I will choose a preferred color, and this will correspond to a number. So all the pixel that I select using the painting brush should be visualized with this color, and will be annotated with this type of ID. So this would be a way for me, and I have to show it as additive here. This would be a way for me in order to draw inside the data set and see the color. At the moment, not seeing what is expected. That is, I should see this pixel being colored. So eventually, so the brush size is okay. I'm doing probably what I was supposed to do, but in general, this should be capable of showing the annotated pixel. It would be a way for manually annotate data. The goal of the plugin is instead try to obtain this in a point-and-click method. So we will rely on the use of watershed. So apologies for this. This is not showing. Should be working. The plugin does not focus on this. So I will delete this data set here. And now what I will do is launch the plugin. So the plugin comes with a description text that lists the steps that have to be followed in order to obtain segmented data. And practically, this is the workflow I've shown in the presentation. So we will start with an image that might have a calibration or might need a rescaling. We will follow with a Gaussian blur, apply threshold, and from this we will get the distance map, seeds, watershed, and a way to measure the object. This type of workflow can be applied to a single population, meaning if my intention was to segment only the nuclei, I would choose this type of protocol. However, I want to try now the two population protocol. It means I will try to use a data set that has a channel that contains DAPI staining and has another fluorescent channel that will contain RNA blobs. So what I'll do now is I will load the data set I have here.
Hi, Rocco. Sorry to interrupt.
Yeah,
We've had a question come in on the Q&A, a request to maximize the Napari window. Um, yeah, just something to keep in mind with.
yeah, sure.
Yeah, thanks.
I'll
Thanks,
do it
Rocco.
now. This is the maximum I can do on this screen. I recognize, some text might be very, very small. So I'll try to explain as we go through. So let me just search the data here. Okay, so in this case, we have two different layers. The first one contains a confocal stack of nuclei. And what we have here in the second channel are RNA spots. So I will first visualize them all together by changing this layer type to additive. And I will assign lookup table. So we will choose the blue for the nuclei. I'll try to increase the contrast. And we will choose, for example, red for the RNA spot. Here should be here. Now, as we go through the Z stack, you can see single slices, and we can switch to the 3D. So in this case, you see the data set appears to be quite flat. It is indeed quite flat. However, it is also a feature of the software that it will load the data set with a not specific scaling. There will be a scaling that is 1, 1, 1 for all the three spatial dimensions. So the first part of the workflow is rescale the dataset in order to insert the correct voxel size. What I will do is I will use this menu, and this menu is has to be followed in a sort of horizontal direction. So it means that all the steps, all these blocks, they will all be referred to one of the layer, while the second part below here will be referred to the second layer that are the RNA spots. So I will do in parallel the segmentation of the nuclei and segmentation of the RNA spots. I am selecting, for example, here one of the channel. Channels appear in the order starting from 0 from the lower one here to the upper one. So this will also help me to select these names of layers inside the menus. So I will select the first one, and I can try to insert a different calibration. So it means, for example, I can try to say this pixel size is 0.25 compared to the Z step that might be 0.5. So in general, what I'm saying here is that the Z is twice bigger than the pixel. These are factors that depend strictly from the image acquisition. So once I do this, you might notice that the first layer gets rescaled and is moved here in the corner. So I'll do the same for the second layer, which contains the RNA spots. I'll try to select 0.25. I'll select this as being 0.5. And this will be the second channel. So it is called channel 1 in my case. Now, both the dataset have the same scaling, and by pressing this house button, we get the canvas to be recentered around our data. So as you may notice, this is still not a very nice elongated 3D dataset, but we have a way inside the software to change the calibration. That is very important because in the end, we want to have results to be represented in units of micron rather than being represented in a unit of pixels. Once I've done this, I can take the first layer, nuclei, and I'll try to segment them. So the first step is to apply a Gaussian blur. So I have this layer selected, and I can choose what is the sigma of the Gaussian blur. The effect of this is that the bigger the sigma, the smoother will be the produced data set. This is needed in order to homogenize a bit the signal that can be very pixelated depending on the acquisition method. This process of applying filter will help the following one, which is create a binary picture of the nuclei. I'm using now as input the blurred dataset, being this one, Gaussian, and I can decide a certain level of threshold. For example, I could choose to use 2000 as intensity in order to create the binary picture. And you might see that moving the mouse here in the bottom part of the software, it will show what is the local intensity of the layer that is being selected. So for the filtered data, we have that the value in this pixel is about 8,000, as you can see, 8.94 E plus 3, so around 8,000 for the brighter one. Whereas when I move towards the edge, I'm going down to about 3.8 thousand, or eventually in the background, I have a level of 200. So this will help me visually to segment the proper value for the Gaussian blur. So I'm starting with 2000. The resulting binary image might be good. So in this case, I will proceed with the workflow. But if this is not what I want, what I can try to do is, instead of using this, I will delete the layer and try to apply a different value for the intensity. So imagine now I go up with 3000. You will see that the binary picture that is created now contains less pixel. So this would be a way in order to get cells that are sort of isolated between themselves. It will help in order to separate them and have proper labels. If I'm happy with this solution, I can proceed with a further step. So this will create a distance map. Every pixel will be labeled, and the intensity will represent the distance it has from the edge. So the picture represented here is a distance map, is visualized in 3D, and can be used in the following block. So here I want to generate a list of points that will be used as seed for the expansion and the creation of labels. So I'm selecting the distance map I produced before and the binary picture, and I can establish what is the minimum distance at which I want to generate those points. So we could start, for example, with a value that is 20, and this will generate a certain number of points. If we think those are not enough, we can try to reduce the value. So we can go with 15, and eventually more points will be generated. Instead, what we needed in this case was less points. So I'll go in the opposite direction. I might try to use 25, and I'll try to delete the previous layers containing points. At this time, I put 25, I generate seeds. The result might still not be perfect. Then there is one way that is handle the point layer that we have here on top. So I will select this tool in order to highlight specific points, now shown in blue, and I can delete this point. Or eventually I can try to take this point here and just position it in the next cell that I would like to see segmented as an independent one. For the other object, I have a point here. This should segment in a sufficiently good way this cell, but I also have a point here at the periphery, which will generate a cell that is is just cut out of the data set. So it's good not to measure it because this could introduce a sort of outlier in the data. So what I can do is I select this point and I can delete it. So this summarizes a bit what could be the manual editing in case the result is not the expected one. Once I have the list of points, I will go through the distance map, select the threshold, the binary picture that will be used in order to complete the expansion from this point towards the periphery of the objects, and select the layer that contains all these points. So with this, I get cells that have been labeled with different IDs, and each object will be then measured. What I've tried to do is I'll show in a grid all these layers that are consecutive steps of the bioimage analysis workflow. So this would be a way, for example, to navigate across different layers and see the result starting from the original image that is here in the top left part of nuclei. Then we have the second channel that we are about to segment in the second part. And then we have these layers. The order by which they appear is the order by which we have them here in the list. So I can just try to move things around if I want to see some pictures side by side. Anyway, the navigation through the different layers is synchronized. As you can see, I can zoom in, zoom out, and try to focus my attention on specific objects. What I will do now is I revert back to the previous visualization. So far, we focused on segmenting the nuclei. So these layers might not be of interest for the moment. So what I will try to do is I will try now to focus on the other channel that is the one containing the RNA spots. So I can hide what is the result of this first part, but those layers will still be here in the list and they can be used. At this point, I will focus on the RNA spots. We have the calibration done at the beginning. We can now choose this channel, which is the 01, and try to apply a Gaussian blur if it is necessary. This should produce a smoother version of the data. So we didn't really need it, but anyway, we applied a Gaussian blur with a limited radius. So this does not change dramatically the data. I will follow with creating a binary image. So I select this last layer being created, and I try to apply also here threshold. So I might start with a value that perhaps is 1000. And if I see that too many pixels are included in the binary picture, I'll do the same operation. I will increase the threshold until only the pixels that I consider be part of the RNA spots are included. So now what I have to do is select the previous layer, delete it because it's not functional for this workflow. I will now go to the creation of a distance map. So select the last binary picture, create a distance map for this data, and use the distance map and binary in order to create a list of points. In this case, it's much better if I have a method that will automatically create points. Previously, we dealt with very few cells, and it was possible graphically to point and click and create these seeds. But now, actually, it is very handy to have an automated method. So you can see that roughly every structure might have one point drawn. And also here, we can tune this parameter. We can try to increase the minimum distance if we think that too many points have been selected, or we can try to decrease it if we think that many points are missing. As well, here we could graphically change the position of points, but it will be requiring a bit of work. So it's rather better for me, in my opinion, to perhaps segment less objects, but make it in an easier way and automated way. I will assume now that this number of points we have generated is enough. So we proceed to the segmentation of objects, selecting the proper distance map of the second channel, the threshold, and the position list that refers to the channel number 1. By doing so, we create, I need to hide this maxima, we have created the labels for every spot. Now, these spots are inside cells. We still need to make a further step, that is relate with parent-child relation. What are the spots that are contained inside each of the nuclei? So I'll go here, make sure the levels are additive so I can see the final result. So you see every cell has a label and every spot has a label now. Now the first step will be relate what cells is the parent of what RNA spots. I do this in the final block here. The final block asks me to identify the labels for to be used for parents. Of course, those are the first labels that we created in the top part of the software. And identify the labels that are the one of smaller objects, children. So I will select this. And finally, I can do a measurement that is a measurement of one of the fluorescent channels. So from the point of view of the RNA particles, what we want to get as information is quantify how big they are, how intense they are, but also what is the parent cell that contains them. So the original channel that I will select for the measurement is the channel containing the RNA particles, the number 1. Finally, I have to establish a directory. So as you can see, I've done a test before. Now what I'll do is simply create a new directory inside this. So it'll be here. And I'll call it CCP test 2. I select this as folder and I click this button. This button should launch the part that segments the object and relate them. So there was a progress bar when we were running before this. And actually the execution was very fast. Of course, the execution time will be slower if we have much larger data set. So I invite you to try with bigger data set and see how slow can be the progress bar. At this point, what I'll do is I will go to the folder here that we had was CCP test, CCP2. So I'll try to open it. It was here. Inside this folder, we now have these files. The first one is a log and contains very basic information. The sigma we have used for the Gaussian blur, the threshold to identify the parent cells, the nuclei, and then the minimum distance and how many cells we have found. The second line refers to the RNA spots. So we have the sigma we have used, the threshold, the minimum distance, and how many objects we have found. Now, for every object here, the results contain much more information. So I will have this CSV file being created. And here we will have, for example, the label of the parent cell. We will have 1, 2, 3, 4 cells, while the 0 should refer to the background, telling us whether we also see sort of unspecific staining or anything that is outside the nucleus. We will have the label of the object. These are the labels of the RNA spot. And we will have basic information, area, expressed in squared micron, being the sum of pixel across the Z stack, the volume being simply the area multiplied by the Z step that was set in the calibration, and then other useful information. For instance, the equivalent diameter being a parameter that says roughly how big would be an object, a spherical object that has the same number of pixels, or the mean fluorescence intensity, or eventually, if we fit the object with an ellipse, what would be the major axis, minor axis, and many other properties. So I believe this summarizes more or less what is the purpose of this plugin. It is offer a very simple way to click through buttons and obtain 3D segmentation, measurement, and relation of parent and child object with application that could be, for example, count how many RNA spots there are in every cell. So with this, I think my live demo is concluded, and I thank you very much again, everybody in the audience, and I'm open to questions.
Lovely. Thank you, Rocco. Thank you for your excellent talk and your incredibly calm delivery of a live demo. That was very impressive. So yes, we now have 15 minutes or so left in our webinar today to have some questions. You can either raise your hand and I should be able to unmute you within the participant panel, or alternatively, you can add your questions to the Q&A panel and I will read them out. So to begin, we've had one question come in from Richard Demetz. The question is, what is the development roadmap for the plugin? Is there ever going to be an AI chatbot in the plugin to guide the user or even find the different parameters for good analysis?
So thank you very much for the question. Actually, the plugin was developed when the advent of large language models or chatbot was probably not really mature as it is now. So it is indeed something that I guess would be possible. There are already plugins that implement the use of large language model in order to create graphical user interface. One of these that comes to my mind is the Omega plugin by the group of Loïc Royer. And I think that is great work and maybe much more advanced of what this plugin is. I suspect that if you have a chatbot, it might try to suggest you what are the best parameter you could use. So far, I don't have any plan for this, and I also would need to do a lot of work in order to implement this. Eventually, what is I think the part that will be needed is that the chatbot would need to have access to the data. In other words, if I apply Gaussian blur with sigma 2, there should be some sort of metrics to estimate whether the Gaussian blur can lead me to segment successfully the cells. So I don't know what is the state of the chatbot, large language model, or in general, the AI tool in order to guide this. But so far is the experience of the users. Just look at the data, maybe look if the pixel intensity distribution is quite homogeneous in the Gaussian blurred image, and then estimate. Yes, it is easy to create a binary mask. But at the moment, I don't have a metric that would say, yes, I feed the chatbot with this metric, let's say the variance of pixels or any other numerical, how to say, estimator, of how the distribution of intensity it is, and, train the bot on this. Perhaps the bot can be trained, or the AI model can be trained on existing data that have been segmented. So it's very important the use of this database where people simply archive example of image analysis workflow. It is indeed a very good question and indeed a good inspiring plan. Point is having time to implement it. So thank you very much.
Great. I am keeping my eye on the Q&A tab. There's nothing in yet, so let me ask one of my own questions. And perhaps building on that last question, so I think you raised an interesting point there about the availability of other plugins within the Napari environment, for instance, Amiga, and that builds on the last question about using AI in this context. So perhaps a slightly more general question that's related, and perhaps for some of the audience who might not be so familiar with Napari or may not be using it within their own analysis pipelines yet. I wondered whether you could speak to some of the other benefits of doing analysis within the Napari environments.
So for me, everything was based on the fact that Python is a sort of simple language to start coding. I have experience with other programming languages, and there are perhaps other benefit in terms of speed or the organization of projects that might be guiding expert coders towards the use of C or towards the use of Java. However, Python is very immediate to learn and allows people with a very low coding skills to start developing their own products. So the environment is very rich of libraries. We saw this specific plugin relies on scikit-image, NumPy. So there are tools out there that allow people to simply simplify their image analysis. And for me, this was the pushing reason to use Napari. It's a viewer for Python that you can enrich with your own coding. So whether you want to use it in a very simple way by clicking buttons in an existing plugin or develop your own code script and call Napari within that, or develop your plugin, it gives all this possibility at once. So this was the reason for me to strongly adopt it as a bioimage analysis software.
Yeah, yeah. So the GUI, the plugin ecosystem, and the capacity to build it for your own purposes as well. Yeah, yeah. Um, Again, perhaps a slightly tangential question. I wondered, so we've obviously focused a lot on the technical aspects of using the plugin and Napari today. I wondered if you could speak to any of the biological insights that either you yourself or collaborators you've worked with have developed from the use of your plugin.
What do you mean the applicability or
Yeah,
what I
so I
think could be
wondered
useful? Yeah.
whether you're aware of any biological discoveries that have emerged from your work. It would be exciting,
Um,
interesting to know.
well, unfortunately not, but I think is within the what I say the reasonably limited aspect of the plugin. It does something very simple, which is segment things in 3D and relate them, count them. So I've tried to use it for some of the image analysis I do as a straightforward method. Perhaps we still didn't arrive to the publication level, but yeah, it does something very simple, 3D segmentation and relate big object with small objects. In my view, it is good because this is done within Napari, which is widely adopted as a platform, and also allows people to use the function. We say the way I implement it is with decorators, so one can simply access the same function without decorator and implement this in Jupyter notebooks. So it gives the advantage of both the worlds. Graphical, if one has no experience, or scripting, you can access the same thing. And it's a strong point of open source software, the possibility to use elements, blocks of code, or part of the tool that is perhaps is underexploited because in many research contexts, people move towards easy commercial solution that ends up to be, sort of black box, and you don't really know what is the method used there. So it does few things, but it's open source. and can be both graphical and scripted.
Mm-hmm. Um, Building on that question, I wondered, is there a standard mechanism how you as a developer of the code can capture information about the use cases and applications that people are using your plugin for? Because I could imagine that that would be really powerful from your perspective of, understanding the impact that you've had, the motivation, and potentially the edges of the plugin's utility as it stands. So perhaps informing future development. Is there a standard mechanism for capturing that information?
So what comes to my mind is there are statistics, for example, of download or installation, and these are in the Napari app plugin. Not sure whether that method captures also sort of more detailed information, like, for example, it was used for this type of data or not, because this could be more a feedback from user. I do receive feedback from users, might be users in our platform or might be users that we train through the Numerous workshop we do also together with Martin and other colleagues. For me, it's really the in-person feedback of users trying to use it that tells me what are the application. Running several workshops give a unique possibility. You get to know new people, new researcher with data set that you never tried before. And surprisingly, the plugin, can work, to obtain very basic results like this, segment objects, relate them. So this is the way that informs me. There is no database or, let's say, online method to get such data so far.
Mhm. Do you think that that might be something that could be useful to have?
Yeah, it could be. Perhaps this could be linked to the existence of database like the BIII we mentioned before, where community just highlight tools and the users, the first-hand users, will comment about a tool can be used for a specific workflow. So I really encourage the community also when we do workshop, we encourage people to say, you have learned something new. Now it's good for the community if you give something back, go on the image.sc website, the forum, in order to post some example or perhaps go into this database and try to enrich the number of available page with your feedback about software.
Yeah, that relates to one of the other questions that I had noted to ask you, which is what would you say are the best sources of further information and training about Napari?
So definitely for every tool, I would say is the image.sc forum. And then connected to this, there are many pages linked to GitHub repository. I make an example that is very close to me, which is the NuBias GitHub repository. We're trying to do something similar also with GloBias GitHub repository, trying to link their training materials that we create to run, many workshops around the world. So it's a good example. You can try to follow these communities, visit the website, image.sc, NuBias, GloBias on GitHub pages, and try to see what is available already out there as training material. It could be used for personal education, let's say, or it could be used in order to run your own workshop in your institution. So someone maybe has done already the work of collecting information.
Fab. Yeah, we could share some of that in some of the comms from this talk. Lovely. Okay, I don't think we've had any more questions from our audience coming on the Q&A channel. So as we're just going into the last couple of minutes, I will wrap up and say thank you very much, Rocco, for your talk today, for sharing your experience and expertise and your fabulous plugin. And thank you to all of our attendees who've chosen to spend their lunch break with us this afternoon. We hope you found the session useful, and I look forward to seeing you at our next session next month. We will be having one of the developers, Cameron Shand, come from who's based at the Crick, speaking about his work on the AI on demand interface. So stay tuned to our various communication channels to learn more about that upcoming talk. So thank you again, Rocco, and see you all next month.
Thank you very much, everybody. Thank you. Bye bye.